what we would like is, can we have some kind of simple confirmation that the Verilog that got generated actually does what we wanted it to do. Okay. Now this is something called equivalence checking. In the general case, equivalence checking says that I have two versions of a design, I need to check whether they are doing exactly the same thing. Okay. And think about it, it is not at all obvious that that is actually happening, because what you had originally was there was a C code, now what you have is a Verilog code. What proof do you have that they are actually both doing the same thing, except for the fact that Xilinx basically gave you some assurance that their compiler works, right? The unfortunate part is there can be situations where the compiler has bugs in it and actually generates Verilog code that does not work the way that you expect. Okay. So there are multiple ways of doing this kind of equivalence checking. There is one method called formal equivalence checking, right, which essentially says there are formal methods by which you can literally say you have the C code, these are the set of transformations that were employed by the compiler in order to convert that into Verilog, and by going through that process you can literally say that this line of Verilog corresponds to this input line of C, and therefore they are exactly functionally equivalent. Whatever the C code does is exactly what the Verilog code will do. In general, that is very hard to implement. We do not have such formal equivalence checking implemented over here. What they do provide, on the other hand, which is much simpler to implement, is functional equivalence checking, right. What that means is you already have a test bench, why not run that same test bench against the generated Verilog code and see whether the same results come out, right. As you can imagine, that is not bulletproof. There can be situations where your test bench was incomplete, you did not really test for some corner cases, and therefore you miss out on some situation where the Verilog code is actually wrong, right. But provided that you have done your homework and you have got the test bench fairly comprehensive, then you can say that yes, whatever was generated by the C code and whatever was generated by the Verilog code, they match, therefore the Verilog code does what the C code was supposed to do, they are equivalent. Okay. That is where this whole business of C and RTL co-simulation comes into the picture, right. So if you click on this, what you get is you can select the type of simulator you want, you can also select which RTL, whether you want to use the Verilog or the VHDL model. It should not make any difference because both are supposed to be exactly the same code, right. If they ever give you a different result, then it means there is a serious bug in the compiler somewhere, right. So hopefully that should never happen. One interesting thing that you should try is the default over here for this dump trace is set to none, okay, but you can change it to all and compile it, okay. You just click on OK, it will run. Now I am not going to do that because it takes some amount of time, I have already run it, right. Therefore I will just show you the final result. If you have selected this dump trace and set it to all, and it successfully passes through the entire compilation process, what you will see as a result is that actually, so what will happen is there will be one simulation report over here called FFT COSIM, which finally comes up with this set of values over here, right. What it is saying is it did the co-simulation, and as a result of doing that it was able to find out that the actual measured latency was 511 clock cycles, measured interval between successive inputs was 512 clock cycles, okay. So this is a case where the interval is one more. Effectively what it is saying is you have to wait for the complete latency, then wait one clock cycle and then give the next set of inputs, right. Fine. So this is a number that you have. What's even more interesting is if you actually open this wave viewer, right. So this is another one of those tiny buttons with some green squiggles on it at the top. When you open this, you actually see that the complete waveform of what is the input that was provided to your Verilog code and what is the output that was generated as a result, okay. Now this is interesting. If you think about what is happening over here, what Xilinx has done, what the tool has done for you is it took your C code test bench and your Verilog code that was generated, the FFT block that was generated as Verilog code, whatever arrays that you were passing into the Verilog code, it created an equivalent interface module which allows the Verilog code to retrieve the data coming from C one clock cycle at a time. So it effectively implements a memory interface between your C code and your Verilog code, right. This is not as trivial as it sounds at first, because C has no notion of a clock. There is no concept of time in the C code that you write, whereas the Verilog code fundamentally has to work only with a clock. Okay. So all that is taken care of, and what you see once you do this is, unfortunately that's not really readable, so I would suggest you go back and run this on your own. I will expand these signals for you. At least once you expand it, you will get a better picture of what's going on. This top level over here is something that says design top signals. Okay, so let's open that and let's see what is there. The first one over here is the C outputs, then the C inputs, block level IO handshake, reset, and clock. Okay, let's start by looking at the clock. It's nothing fancy, it's just basically a clock. It's a square wave, right? The only interesting thing about it is, if you look at those numbers in the on the top over there, which again unfortunately are not readable. In this case it says 1005,000, so it's basically telling you that it's 1,000,005 picoseconds or 1005 nanoseconds. Okay. The interesting thing is, as you sort of step forward over there, you will see that it goes in steps of 5 nanoseconds at a time. The reason for this is, while doing the synthesis, you had specified a 10 nanosecond clock period. Automatically Vivado HLS uses 10 as the target clock period for your synthesis and implementation. Okay, good. So all that means is it's using the right clock. What's it doing with the reset signal? Let's zoom out fully over here. You will see that there is just one tiny bit in the corner out here where the reset is equal to 1, right. So within around 100 nanoseconds or so, right, by the time you reach around 100, 120 nanoseconds, the reset has already gone high and then gone low. Okay. This is an active high reset, so during the time that it is high, the module that you generated is being reset. Why is it for 100 nanoseconds? That's just some standard that they use. Okay. They want to make sure that if at all there is some kind of a synchronous reset that requires multiple clock cycles, everything will get reset properly. Okay. Again, you don't need to worry about this. Now let's look at the C inputs. This is interesting. Effectively what it's telling you is, what this is showing you is the data underscore in, which is a memory interface. Okay. You can see that there are a lot of these yellow up and down squiggles that you see over here correspond to when the chip enable signal going out to the memory block, right. So there is a data in address and a data in data coming back, right. For the other one, there would be a data out address, a data out data going in this direction, and a data out write enable, right. In the case of read, there would also be a data in chip enable. Similarly, there would be a data out chip enable as well that goes out over here. Okay. So those are the signals that we see. So this highlighted line over here essentially corresponds to the data in chip enable. There are separate signals for imaginary and real. That's because the complex value is basically treated as two memory ports. In principle, I could read separate real and imaginary values corresponding to different addresses. Very unlikely that I would ever do anything of that sort. So in practice, what is usually done is, there is something called a data pack directive that you can give to the HLS tool, which will basically combine the real and imaginary together into one 32-bit value. Why is that good? Because it reduces some complexity. You don't need two addresses, you don't need two write enable and read enable signals and so on. Okay. The interesting thing over here is when you look at the addresses that are generated, right, if you can make out that blue value that is written over there, right, effectively what you can notice over here is the order in which the data are being read back are being read is 0 followed by 16 followed by 8 followed by 24 followed by 4. Why? That is the bit reversed addressing, because the first block itself is doing bit reversal, right. So effectively what is happening over here is the very first block is doing bit reversed read, okay, which means that the way that it gets implemented is the addresses going out for the very first set of reads itself are in bit reversed order. So it gets the data back in this format, right. What you can do with this other signal, the imaginary signal for example, is you can right click on it. There is an option over here that allows you to change the radix, okay. You can set it to real and basically say it is fixed point signed with the binary point at 8, okay. And if you look more closely at the data at that point, it basically starts telling you that these values are actually, for example 0.05, 1.015, minus 0.89, minus 0.60. You correlate that with the input text file that we gave, they match exactly with those values, okay. Zoom out fully, let us look at the big picture. You will see this clump of activity at the left side, inactivity for a long period of time, again a clump of activity, right. So what is happening over here? Basically what is happening is that clump of activity on the left hand side is where the FFT module that you have created is reading data from the test bench, okay. How long does it take? You can sort of put markers at the beginning and at the end of that, and you should see that it takes probably 96 clock cycles, right, basically corresponding to how much time the bit reversal is going to take to read all the values, okay. After that it is sitting idle for, well, it looks like nothing is happening for a long time, and then suddenly it starts reading data again. Why? The best way to understand that is go look at the outputs. You will see that this region over here corresponds to the part where the outputs are now being generated, okay. So it got all the inputs, did something during which time neither inputs nor outputs were being affected, and then finally started generating outputs, okay. The outputs also sort of take a similar pattern, the write enable and the chip enable and the addresses, all of those you can look at them and see exactly the patterns and the values that are coming out, okay, and compare them with what you expect from your C code and make sure everything matches, right. And the interesting thing over here of course is as soon as all the outputs have been generated, we are ready to start reading the next set of inputs, okay. So effectively what is happening is this test bench is going into a cyclic mode of operation. It basically reads in the next set of values as soon as the first has completed. Why does it do that? It does not really need to do it, but it helps. We will look at why a moment later. The other interesting set of signals is this third row here, which is called block level IO handshake. Let us open that and see what it is. You can essentially see that there are 4 signals over here. The first one is AP underscore start, okay. What that means is the test bench is going to give a start signal to your FFT module after a certain amount of time. Then there is a done signal which the FFT module should return after it has completed operation. There is an idle signal which basically, as long as it is 1, it means that the core is not doing anything, it is ready to do some, you can basically try and give it new inputs. And the ready signal, which is once again indicative of whether the core is ready to accept new data, okay. So let us zoom in a little bit. On the left hand side what we find is soon after the reset has been removed, right, the start signal goes high. As soon as the start signal goes high, the idle signal goes low, okay, computation starts. The done signal is low at this point, it is 0, and the ready signal is also 0, basically meaning that it is not really ready to accept any new data at this point. Now this ready signal can be a little confusing. How did I give a start signal without seeing a ready signal equal to 1, right? If you look at how it gets implemented, then it turns out that the ready signal sometimes comes only as a response to the start or the valid signal from the other side. So in some cases this can be a little confusing. To understand it properly, you will have to go back and look at the Verilog code to make sure it's doing the right thing. Let's go all the way to this point out here. What's happening is, after a significant amount of time, the done and the ready signal both become 1. Okay? For how long? Just for 1 clock cycle. So effectively it is one state where the done and ready signal basically say, okay, going high, and after that, because this test bench is set up in such a way that as soon as it sees a done signal, it will start the next set of data. The done and ready signal go back low again. You will notice that the start signal was kept high throughout. I didn't sort of give it a pulse and then bring it down again, because the standard operating procedure for these modules is, if I leave the start signal high, and once I have started operation, I have anyway got out of that initial state. So I am never going to look at the start signal again until I am back in that initial state. So if you do make the start signal high and leave it high, all that it means is, after it has finished one computation, when it goes back to the init state, it will immediately start doing the computation again. Right? So in a lot of cases, you will find that it makes sense to just connect the start signal permanently to high and let the data flow through as and when it is ready. Okay? You can measure these values, right? Once again, I would encourage you to go and try that out. Find out the clock cycle number at which the done signal became high, compare it with the clock cycle at which the start signal was made high. That difference in clock cycles is your latency. Okay? That plus 1 is your initiation interval. Okay. Alright, so far so good. I am going to close this. But just for completeness, I also want to show you another variant of this same design, where I have made a couple of optimizations, right? Like I told you, I am not telling you what the optimizations are, it is just things that you can probably figure out, and anyway we will be discussing later. The interesting thing is, now look at the time period. The interval is 21 clock cycles. So from 511, we have managed to bring it down to essentially 20 clock cycles. Okay? Which means that this is a 32-point FFT core. Every 20 clock cycles, I can start giving it new data. It doesn't even require 32 cycles to read the data. So effectively, that must mean that it is going to read at least 2 values per clock cycle. Otherwise, it can't, even read the data within 20 clock cycles. Okay? But with every 20 clock cycles, I can give it a new block of 32 values, right? And it has a latency of 83 clock cycles as estimated by the tool over here. Okay? Now, one thing that you will see is, I ran the co-simulation for this. The co-simulation gives me slightly different numbers. It shows that the interval over there is 20, not the 21 that the synthesis estimate told us. And the latency is 124, not 83. Okay? Why these differences? Because the co-simulation is actually implementing the memory block and so on, and measuring the difference between start and done signals. Whereas the other one is just sort of estimating based on what are the delays of each individual module and adding it up. There could be errors in how it is estimating it. Usually not much, so you don't need to worry about that typically. What happens if you open the waveform for this? I am just going to show you the block level handshaking signals alone because they are illustrative, right? Without really worrying about the rest of the, you can look into the rest of the signals by yourselves. Design top signals, block level IO handshake. AP start, the start signal is sent high and remains high throughout. The idle signal goes low soon after the reset is removed and just remains 0 for the rest of our simulation. What is interesting is, now the ready and the done signals are behaving differently. Okay? So first things first, the ready signal that you can see over here, there are a number of spikes in it. If you measure the difference between this time and where the first start signal was given, 20 clock cycles. So that is your initiation interval. Okay? And it pretty much, it's sometimes 20, sometimes 21, it sort of varies a little bit based on what all the other handshaking signals are going through, but for the most part it is fairly consistent. Okay. Where is our done signal? Here it is. Okay. So, the difference between the done signal and the start signal corresponds to 124 clock cycles. That is where it got the measured latency from. Okay. And you can sort of see that 20 plus 25 times over here plus something else, this is around 124 clock cycles. Okay. So, the way that the test bench works is, because you had only given it one FFT call, it still puts it in a loop until it is able to at least measure the one done signal. Okay. So, if for whatever reason your Verilog code hangs and is not terminating, not generating a done signal, your simulation will go into an endless loop, right. So, there can be situations where you actually end up not crashing even, but just sort of sitting there simulating endlessly. Okay. So, those are all things that you need to be aware of and catch if necessary. But this sort of very clearly indicates the difference between latency and the pipeline initiation interval also.